So in previous videos, we built the control logic for our computer, which consists of a couple EEPROMs, basically, that are taking the instruction from the instruction register, as well as the step that we're on using this step counter to output a control word. And so these EEPROMs are programmed with microcode that, based on the instruction. So if we have a load A, which is what we have here, 0001 is the opcode for load A, then based on each step, so for the fetch cycle, step 0 and 1, and then for the load A, step 2, 3, and 4, it sets the appropriate bits on the control word, which is right over here, and you can see it sequencing through those bits on the control word. And so when we set this up originally, we manually programmed these EEPROMs just by setting the appropriate input pins manually for each address. In this video, what I want to do is use the Arduino-based EEPROM programmer that we built in a previous video to make it a little bit easier to program these EEPROMs, which will make it a little bit easier for us to add more instructions other than just the few that we've added so far. So just as a reminder of what we're trying to do, we've got 15 bits in our control word, and we could add a 16th here, which we'll do in a future video for something. And so these are split into two sets of really 8 bits across the two EEPROMs. And then the address lines of those EEPROMs are, there's 3 bits that indicate which step we're on, and then we've got the 4 bits here which indicate which instruction we're executing. And for the first 2 steps of every instruction, doesn't matter what instruction, we have these two control words that fetch the instruction from RAM and increment the program counter. So if we want to program that into our EEPROM, we've got our EEPROM here in our programmer that we built with the Arduino. And the code that I'm going to use, this is just the same EEPROM programmer code that we used before when we built the programmer to start with. And so we've got a few functions in here. So we have a set address, which sets the address bits and the output enable signal on our EEPROM. And then we've got a function here that reads a byte from an EEPROM if we give it an address. And we've got a function here that will write a byte to the EEPROM if we give it an address and then the byte that we want to write. We've got a function here that just prints the contents of the EEPROM, or at least the first 256 bytes. Here's where we are actually going through and programming it. This is the code that we had before, where we were writing in some data to build that 7-segment display decoder using the EEPROM. So I'm going to get rid of this because we're going to be writing different data this time around. And actually, instead of saying the data is going to be an array of bytes, because our control word is 16 bits long, what I'm going to do is I'm going to actually set up our data to be a 16-bit value. And then when we actually write it to the EEPROM, we'll pick whether we want the first 8 bits or the second 8 bits, because we'll want to program the first 8 bits into the EEPROM on the left, and then the second 8 bits into the EEPROM on the right. But just to kind of organize things, what I'm going to do is I'm going to redefine data as an array of 16-bit values. So the data type is going to be uint16t, and so this means this is just an unsigned 16-bit integer, and it's going to be an array. And we're going to put some data into it. And so I'll get rid of all of this stuff because we're not building a hex 7-segment display decoder. So for data here, basically what we want to do is just replicate the data bits that we have here that we want to program in. And we can just kind of go one by one. So this first value here, we can even enter it in binary. So we can do 0b, and that tells it that we're giving it a binary number. And then I can just enter this binary value that we've got right here. So let's just do that. So that's that first value. So it's 16 bits, and the second bit here is set. That's the memory address register in bit. And then the second from the last, which is actually the third from the last, because remember this is 7 bits, and there's going to be another bit here that I'm going to use in a future video, but for now we want to make sure we just set these last bits here to 0. So it's this third from the last bit is a 1 as well. So that's this first value here, right? So for instruction 0, step 0, we're writing that binary value. We can do the same thing for the next address. And so here we've got 3 bits set. So this is the RAM out, this is the instruction register in, and then this is our counter enable, which increments the program counter. So that's this control word here. Now we could keep defining all of these just like this, just one by one, although you can imagine this is starting to get a little bit confusing because we've got all these binary values. So what I'm going to do is I'm going to define some constants that's going to make this a little bit easier. So what we can do is we can define a constant for each of the actual bits, and then we can combine them. So the first bit here is the memory address register in, or the MI. And that's going to be just this second bit here. And so the rest of the 14 following bits are all going to be zeros. And then the other bit that we're going to have set in this first word here is the counter out bit. And that's the third from last, because remember there's an extra 0 here. So I can define CO as, 0B for binary. And it's going to be all zeros except for that bit is going to be a 1. And that's our counter out bit. And then in our data, for that first word that we're putting here, rather than defining that in binary, I can use these two things that I've defined, the MI and the CO. So I can say MI, and then I can do OR, which is this pipe symbol, CO. And what this will do is this will bitwise, this vertical pipe symbol in C is a bitwise OR operator. And so what it'll do is it will take these two values and it will do an OR of every bit. And so 0 or 0 is going to be 0, 1 or 0 is going to be 1. And so that'll give us a 1 here. And then the rest of these bits are all 0 or 0, so those are all going to be zeros. Except here we're going to get 0 or 1, and that's going to give us a 1. And so if I do MI, bitwise or CO, I'm going to get a value that has the MI bit set and the CO bit set. And so that will be a nice shorthand way of saying exactly what this binary value here is saying. It's saying that the MI bit is set, and it's saying that the CO bit is set. Then for the second value here, rather than having that in binary, I can do the same thing. So that's going to be RO, so RAM out, instruction register in, and counter enable. And of course I need to define those, and in fact what I'll do is I'll go ahead and define all of the bits. So the first bit is the halt. I've already got memory address register in. So next I'll do RAM in, RAM out, instruction register out, instruction register in, A register out, sum out, the subtract bit to tell the ALU that we're subtracting instead of adding, B register in, output register in, counter enable, and then we already have counter out defined, so we have just the jump, and then that last bit we won't define just yet. So now we've got all of our bits defined, and so we can write our microcode using these terms. And so for the first instruction, or really the 0th instruction, we haven't actually defined that here. So so far we've just defined the load A, add, output, and then we did halt as well. But load A, the instruction, the opcode for it is 0001. We don't have anything at 0000, but we still want that fetch. So we'll do those first two steps. So the first step is memory in, counter out, and then the second step is RAM out, instruction register in, counter enable. And so for the rest of instruction 0, we'll just have all zeros, so it won't do anything. So I'll add 6 zeros, because each instruction can have up to 8 steps, right? Because our step input to the EEPROMs is 3 bits. And of course we reset it after it gets to 4, it resets back to 0. So we only, in practice, we only have 5 steps in our computer. But because it's a 3-bit value, we could have up to 8 steps if we weren't resetting it. And so we need to at least make sure we've got that room in the EEPROM. So we'll just write all zeros to those last 2 steps, but or last 3 steps. So this first line here, that'll be an opcode of all zeros, which it doesn't do anything, so we'll call it the NoOp instruction. So if you wanted to write a program and have an instruction that doesn't do anything, maybe you want to insert a little bit of a delay by running an instruction that doesn't do anything, you can use this NoOp instruction. But instruction 1, that's the next instruction, that's load A. And so we can write that instruction using this same sort of format. So it's like every instruction, it starts with the fetch cycle. So we do the memory address register in and counter out. So taking the program counter and putting it into the memory address register. And then the second instruction in the fetch cycle is always going to be the same. RAM out, instruction register in, and counter enable to increment the counter. Now for load A, for steps 2, 3, and 4, we're actually going to do some things, or at least for steps 2 and 3, we're going to do some things. So at step 2, it's instruction register out, memory address register in. So we can just do IO MI. So that's going to take the address from the instruction register and put it into the memory address register. And then the next step is going to say RAM out, A register in. So RAM out, A in. And that's it. So we can do 0, 0, 0, 0 to make sure we want to make sure each of these instructions has 8 steps. So this is going to be instruction 0001, which we're calling load A. And I'll just line these up. And actually, I'll just line all of this stuff up so that it's kind of easier to keep track of exactly what each instruction is doing. So the next instruction that we've defined is the add instruction. So that's just going to be the instruction 0010. So 0010 is going to be add, and it starts out the same way. Of course, every instruction starts out with that fetch cycle. So memory address register in, counter out, and then RAM out, instruction register in, counter enable to increment the counter. And then for add, we start out with a instruction register out, memory address register in. That's this step here. Then the next step is RAM out. Oh, I'm in the wrong place. The next step is RAM out, B register in. So RAM out, B in, because we're putting the value that we're adding into the B register. Then we take the sum out and A register in. So take the sum out and put it back into the A register in. And then we follow that with our zeros. And I'll just space everything out here so it all lines up. And so that's our add instruction. Now what I'll do is I'll go ahead and add NoOp instructions for the rest of the 16 different valid opcodes, right? So that fills in the rest of our instructions, or at least our different binary values for which we could define instructions. It fills them in with these NoOps, or no operations. So they do the fetch cycle, which of course we need to do for every instruction. Those first 2 steps need to be the fetch. And so we've got those for all of these. But then the other commands that happen for each of these commands we haven't defined yet, but we can start to do that. And so in fact, before we had an output command defined and we had a halt command defined, and output we said was 1110 and halt was 1111. So those are just the last 2 opcodes down here. And so for output, it was very simple. We just said A register out and output register in to take the contents of the A register and put it on the output. So that's that command, that's the output command. So we'll add a little comment over here, that's output. And then the halt is actually very simple. On the first step here, after fetching the instruction, it just sets the halt bit. So that's our halt command. And so these are the commands that we've defined so far, and we've manually programmed the EEPROM with these commands. But you can see it's very easy for us to come in here and add additional instructions to our computer. But before we get to that, let's at least try to see if we can get this programmed onto an EEPROM and see if we can get that EEPROM to work. So for that, remember we changed our array here to be 16 bits instead of 8 bits. So if we go back and look at our code here, first we are erasing the entire EEPROM, which is fine. We can leave that. Maybe we'll get rid of that later because it's kind of slow, but we'll leave that for now. And then here we're programming it. And so we're basically just going from address 0 through the size of our data. Well, we don't want to do this anymore, right? Because our data now, the size of it is not going to tell us how many elements there are in data. It's going to tell us the size in bytes of data. And so now that each element in the data array is 2 bytes, this size is going to be a little bit misleading. So what we want to do is say, divide that by the size of one of the elements in data. So we can just say data sub 0. And so each of the things that we're putting in data, each of the elements in this array is a 16-bit value, or 2 bytes. And so we're dividing by 2. So this should give us the number of elements now. So we're going to iterate through the number of elements. But now when we write to the EEPROM, if we just write data sub address, that's going to refer to the entire 16 bits at that address. But when we're writing to the EEPROM, it's going to interpret this 16-bit thing as a byte, which is 8 bits. So how is it going to interpret this 16-bit value as 8 bits? Well, it's going to look at the last 8 bits, and it's just going to ignore the first 8 bits here. So the way this is written, this is going to work fine if we're programming this second EEPROM, because it's always just going to look at the last 8 bits. And so it's just going to program this column here, which is fine if we want to program that second EEPROM. But if we want to program the first EEPROM, we need to tell it to look at the first 8 bits. And the way we do that is by shifting all 16 bits over to the right, or by shifting all the bits over 8 positions to the right. And so the 8 bits on the right just sort of get lost in that shift. And then these 8 bits on the left get shifted over to the right. And so the way we do that is just with the shift right 8, the shift right operator by 8 bits. And so that'll shift all of these bits over by 8 positions, and then we'll effectively be looking at the first column here. So if we want to program the first EEPROM, this is what we want to do. So let's go ahead and give this a try. I've got an EEPROM in here, so let's upload this to the, whoops, what did we do? Oh, I'm missing a semicolon? No. Oh, I see, I'm missing some commas here. That might be all that was. Let me verify that. Yep, that looks like it's compiling. So let's upload that. And you can see it's uploading. And if we look at the serial output, yeah, it's going to erase the EEPROM first. And that'll take a minute or two, so I'll speed that up. Okay, it'll program it, and then it will output what it's got. And so what we see is we see sets of 8 bytes, right? So we've got 1, 2, 3, 4, 5, 6, 7, 8 bytes. This is our first command. This is our NoOp command. And it's 8 bytes long, even though we only are going to use the first 5, right? So we reset when we get to 5. But even though this counter is only counting from 0 to 4, because we reset it when it gets to 5, it's still 3 bits. And so it has, and so we're taking up 3 bits of our address space on the EEPROMs. So we need to have these 8 bytes here to handle that, even though these last 3 we're never actually going to use because we reset it when we get to here. But we see this 4014 in the first 2 bytes of every 8-byte instruction. If we look at what we're trying to program here, these first bytes here, 0100, that's a 4, and then 0000 is a 0. So that's our 40, and then 14 is the next instruction here. So 0001, that's a 1, and 0100 is a 4. So we get our 4014. And so every instruction starts with that because that's our fetch cycle. So for those first 2 steps, we should always see 4014. And so that's what we see, 4014, and then of course all zeros for our NoOp. And here we see 4014, and then we see 2 instructions that are programmed, and this is for our load A, and then the rest zeros. And then the next instruction is add, so we have our 4014, and then 3 instructions, because add it has 3 instructions, and then of course the rest are zeros, and these will never get executed. And then for everything else, we haven't programmed it yet, right? So it's 4014 and then a bunch of zeros, except for the last ones here. So this is our output, so 4014, and then we have a bit set here, and that's, let's see, the last bit in the first EEPROM, which is, yeah, for out, that's A out, so that makes sense. And then for the halt, 4014, we get 80, and so 8 is 1000, which makes sense for halt, because we want that first bit, which is the halt bit set. So this looks like it worked perfectly well. So if we pulled this EEPROM out of the programmer and used it to replace the first EEPROM in our control logic, it should work the same. So now the second EEPROM, we should be able to program just the same way. The only thing we need to change is, rather than shifting these bits to the right, we just don't shift them to the right. So we just get rid of this. And so that should allow us to program the second EEPROM for these bits over here on the right. But another way we could do this is we could actually, if you look at this EEPROM, we're only using the first 128 bytes of the EEPROM, and then the rest of the EEPROM is blank. But what we could do is we could program the first half of the control word into the first 128 bytes, and then the second half of the control word into the second 128 bytes down here. So then if we're using that EEPROM that we've programmed that way as the left EEPROM, then we just want to make sure we're using the first 128 bytes, which of course is what we're doing. But then if we're using that same EEPROM as the right EEPROM, we want to use the next 128 bytes, and we can do that by setting the address line A7, I guess, is the 8th address line. We have that tied to ground here. If we tied that high, then the rest of the address lines that are selecting the address would be offset by 128. Because this is the 128th place of the address lines. So if we just set that high, that'll add 128 to every address that we input here. And so what we can do is we can actually program both EEPROMs exactly the same, but depending on whether we've set that address line to a 0 or a 1, will determine which function it serves. So that can make it a lot easier to program these, so we don't have to think about which one we're programming. They'll both be the same, and it's just where we insert the chip, and then it'll just matter how we tie this line. So we'll have to change this from being tied to ground, like it is here, to being tied to 5 volts, but that's easy enough. So to do that, what we want to do is take this loop here where we're programming the EEPROM and just duplicate that. So here we're going to program the first 128 bytes, and then here we want to program the second 128 bytes. So what's going to be different is our address. We're going to add 128 to it, just to shift it. And then, rather than shifting right, we don't shift right. And that way the data that we write there will be this second column. So let's give that a try. Go ahead and upload that. And we'll look at our serial output. And of course it's going to erase the EEPROM. I'll speed this up. And now it's programming it. And here we go. You can see it's now programmed the second half of this differently. So we got the 4014 starting out every command just as we did before. But then for the second half of the EEPROM, each fetch cycle is 0408. So let's see if that makes sense. So that would be for this. So 04 would be 0000, that's 0. 0100 is 4, so 04. And then 08, 1000 is 8. So that looks right. So for the second half of the EEPROM, so from here on, it's going to effectively be the microcode for these 8 bits here on the right. So let's give this a try. Let's reprogram both of these EEPROMs and see if we can get the computer to work the way that we want it to. So take power off the computer, and we'll just put each of these chips into our programmer one at a time and program them. Here's our first chip. I'll re-upload that. Okay, there we go. We've programmed our first EEPROM. I'll pop this out, put it back in the computer. And then the second one, we're going to do identically, and I'm just going to reset the Arduino and it should rerun the program. Yep, there it goes, erasing and programming. And now this EEPROM is programmed identically to the other one. I'll pull that out, put it back in, hopefully in the right place. And so now both of these EEPROMs are programmed identically, which means if we power up the computer now, and I'll stop the clock and reset. And so what we see is we see the memory in. Let's look at what we want to be seeing here. So we want to see memory in, but then we want to see counter out. But instead what we're seeing is subtract, which is not what we want. But the reason we're seeing subtract is because we're seeing the same thing on both. So we're seeing the second bit here set, memory in, and then we're seeing the second bit set over here because both EEPROMs are the same. And then if we advance the clock to T2, we see RAM out, instruction register in, which is exactly what we want, but then we see those same 2 bits repeated over here where what we should see is just counter enable. And we don't see counter enable, we see output enable and counter out, which again is just these 2 bits mapped over here. But that's because this A7 on both of these is set to 0. So we're looking at the first 128 bytes on both of these. And what we want to do is look at the first 128 bytes on here and the second 128 bytes on here. So if we just change this 0 on this address line to a 1, we should be doing that. So let's take this jumper out. Let's tying that to ground and instead connect it to 5 volts. And now you see when I connect that address line to 5 volts, this changes and it's now the counter enable bit, which is exactly what we want for T2. So now if I reset back to T0, we see memory address register in and counter out. Memory address register in, counter out. And if we advance the clock to T1, we see RAM out, instruction register in, counter enable, which is exactly what we want to see. So it looks like at least the first 2 bytes in each of these is working just fine. So now let's try programming something that we've programmed before and see if it works. So we'll go to address 0 and we'll do a load A 14. Address 1, we'll do an add 15. Address 2, we'll do output. Address 3, we'll do halt. And then we'll go to 14 and put in a value and go to 15 and put in a value. And let's try running that. And that looks like it ran successfully. And if we reset the computer, it should run again. And there we go. So we've basically reprogrammed our EEPROMs and done the same thing that we did when we manually programmed it, but now we've got a nice way of being able to add additional commands. So let's try adding a subtract command. So if we want to add a subtract command, it's basically going to be the same as the add command, where we want to take the address of the value that we want to subtract from the instruction register, so instruction register out, put that into the memory address register, so memory address register in. Then we want to take that value that we fetch from memory, so RAM out, put it into the B register, and just like the add command, we want to take the sum out and then put that back into the A register. But instead of it being the sum, we want to subtract. So we just set the subtract bit. And setting that subtract bit will make the ALU subtract instead of add. And so otherwise, it's just the same. And I'm just going to add some extra spaces here to make this pretty. So there we go. So that adds a subtract command, which is 0011. And of course, next we need to actually program our EEPROMs with that new microcode so that the subtract command will be available to us. So we can do that just like before. So we'll power that off, and we'll pull the EEPROMs out and one by one program them with the programmer. So there's our first EEPROM, and we'll upload the code and go to our serial monitor, and it's erasing, which I'll speed up. And now it's programming, and there we go. So now that should have the subtract command in it. So I'll pull this out, put it back, and get the next one, and program it as well. And I'll just hit reset, and it'll rerun the program. And it's erasing, which I'll speed up. And I guess I could get rid of the code that erases. I don't know why we need to erase it every time, because we're just going to be writing over all the stuff we care about anyway. And we're programming this one, and we're done. So now the second EEPROM is programmed, and so we'll put it back in like that. And so now we'll power up the computer again, stop the clock, and reset everything. And so now we have a subtract command. So let's write a program, and let's say for instruction 0, we're going to say load A 15. Then we're going to add 14 and subtract 13, output the result, and then halt. So this is our program. If we want to then assemble this program, so this is assembly language with these mnemonics. So to assemble this into the machine code, in address 0, we want to put a load A 15. And so load A, if we come over here, is opcode 1. So this is going to be 0001, and then the operand is address 15, so 1111. Okay? Then we want to do an add 14. Well, add is 0010. So 0010 is our add command, and we want to add 14. So 14 is 1110. Then we want to do a subtract 13. And so subtract is this command we just added. So the opcode for that is 0011. So 0011. And then the operand is 13. So that's 1101. And then output, we can come over here. We also have our output command is 1110. And it doesn't take any parameters, so we can just set this to all zeros. And then the halt command is 1111. So 1111. And it also doesn't take any operands, so we can just set those to all zeros. So this is now the binary representation of this program. And we also need the data, right? Because we're saying load something from address 15, add something to it from address 14, and then subtract something from it that was in address 13, and then output the result. So I guess the question is, what math problem do we want to do? So we could just say, okay, well, we're going to load a 5, add a 6 to it, and then subtract a 7 from that. Just making up numbers here. So if we load a 5, add 6, and then subtract 7, that should give us a 4, right? So let's put these values into memory. So 5 is going to be 00000101 is 5, and then 6, 00000110, and then 7 is 00000111. So we'll just program those in. Of course, we can put any values here, and that'll be the numbers that we're loading, then starting with, adding and then subtracting. So 5 plus 6 minus 7 is what we're doing here, so we should get 4. So let's go ahead and program this in and see if our subtract command works. So we're going to program mode, we're at address 0, and we want to do our load A. So let's program in our load A 15. There it is. Now we go to address 1, and program in our add 14. So we do add 14. And there it is. And then we go to address 2, and we want to do subtract 13. So that's our subtract and a 13. So there we go. 0011 is subtract, and then 13. Now we want to go to address 3 and output the result. So 1110 is our opcode. So address 3, and we have output. And then address 4, we'll put our halt command. Okay, so that's the program, and now we need the data. So if we go to address 13, so 1101, we can put our 7 in there. And then address 14, we'll put our 6. And finally, address 15, we'll put this 5. So there's a 5. So we'll go back to run mode, reset, and well, I guess I'll just let it rip and see if it works. So if we're going to load from address 15, that's a 5. We're going to load a 5. We're going to add a 6 to it, and then we're going to subtract a 7 and output the result. So we should get a 4. So let's see what we get. Hey, there's a 4, and it halted. So it looks like the subtract worked. And so now hopefully you can see it's pretty easy to come in here and add all sorts of different commands based on the different control signals that we've got available to us. And we can fill in the rest of these with whatever commands we want or whatever opcodes we want to add to our computer we can do. So in the next video, that's what I'll do, is I'll fill out some more of these and start writing some more complex programs.